Let's take a look at the first part of section 5, which is systems of linear equations and inequalities. This should all be review, so hopefully pretty straightforward, but we'll freshen up on our skills. So recall a systems of equations is where we have two or more equations with the same variables. So if one equation has x and y, the other equation needs x or y. We will focus on two variables today, so that means we'll have two equations. Now, a solution of a system is the ordered pair or pairs that satisfy all equations. So if I plug it into one equation, I get a true statement, and I plug it into the other equation, I get a true statement. So let's remember how we solve by graphing. Well, when we're graphing, we will have three different scenarios that happen. Okay? The first scenario is that we could get intersecting lines. So for example, one equation gives me a line that looks like this, and another equation gives me a line that looks like that. Okay? Clearly, these lines are intersecting, and where they intersect is the solution. So what that means is that when we have intersecting lines, we have one solution. And we would write that as an ordered pair. We also have some vocabulary to go along with that. When we have one solution and the lines are intersecting, we call that a consistent and independent system. Okay, so we're consistent in the fact there's a solution, but we're independent because the lines differ from each other. The second scenario we could have is that we have coinciding lines, aka the exact same line. So for example, here's one equation graphed, and then when I graph the second equation, it happens to be right on top of that. So they're the exact same lines. When we have the exact same lines, our intersection points are everywhere, and lines go on forever to positive infinity and negative infinity. So the number of solutions we have is infinitely many. Please do not put the symbol infinity. That means an actual location. Infinitely many is the number of solutions. Also, don't write all real numbers, because notice, like this ordered pair and this ordered pair are not part of that solution. So we don't want to say all real numbers. We want to be specific that there are infinitely many solutions. The classification for that is a consistent and dependent system. And our third scenario is that we have parallel lines. So for example, here's our first equation, and here is our second equation. The lines are parallel, which means they never intersect. So how many solutions would that be? 0 solutions. That classification is an inconsistent system. Okay, so I'm going to have you practice solving by graphing. I'll set it up for you. So we're going to graph our two lines. Remember, we always want to put those in slope-intercept form to graph. So we'll subtract 3x, divide by -2, and y equals positive 3/2 x plus 3. The second line, and I'll put that in orange, is where we'll just subtract x. So we get -x minus 2. Now that you have your two lines, you're going to go ahead and graph those. So practice graphing our two lines. If they intersect, state the ordered pair. If they don't intersect, that would mean no solution, so state that. And if they're the same line, make sure to write infinitely many. Then also be sure to classify with the correct vocab. So give that one a shot. How about systems of inequalities? So we're going to graph these very similarly, except for inequalities have more answers to them, right? We don't have to be an exact value. Being greater than or less than gives me a much wider range of possible answers. So when we are graphing systems, we're going to graph our boundary lines, but the solution set is represented by the overlap, and I should have made this a little longer, overlap of shading of the graphs. Okay, so we're going to graph our lines. We're going to make sure that we use a solid or dotted line for boundary. If we're included, so greater than or equal to, or less than or equal to, we'll use a solid line. And if it's just less than or greater than, we'll use the dashed line. Then we're going to use a test point to shade. And after we do both of our equations, we'll look at the overlap. So I will do number 2 with you to refresh yourself a little bit on some special case lines. So if we look at number 2, we actually have 3 inequalities. So the first one, when we just have an x, remember when it's just an x, that's going to be a vertical line. So I'll use blue for that one. I go to where x is 2, here it is. And since it's a greater than symbol, I'm just going to have a dashed vertical line through where x is 2. Now I need to do shading. So I use a test point. Pick a point that's not on that blue line. Let's pick 0. Is 0 greater than 2? No. So since this is where 0 was, and it's not a true statement, I do not want to shade that side. So what I'm going to do is shade over to the right of that vertical line. Okay? From there, I'm now going to plot the next one. I'll use orange. When I just see a y, that's a horizontal line. So we'll go to 4 at my y, and I'm going to have a solid horizontal line because it's saying less than or equal to. Remember to extend your lines completely. If you just do short little segments, you're going to have a hard time figuring out the overlap. Now this one says y is less than. So I'm going to pick a y value. If I pick a y value of 0, is 0 less than 4? Yes. So that means my shading for all the orange will be below. If I just had these 2 equations, I would just focus on the orange and blue. So far, my overlapping is in that sort of bottom right area. But lastly, we do our third line, and I'll use green for that. This is going to be a diagonal, right? It is going to be in y equals mx plus b form. So we plot our y-intercept of -2. I'm just going to use a green point here so you know. -2, and our slope says to go up 2 over 1, up 2 over 1, and so forth. Again, you want to make sure that your lines aren't short and little segments, but extended. I'll use a solid line here because it's saying greater than or equal to. And now we do a test point for shading. So the ordered pair 0, 0 is not on that line, so I can plug in 0, 0. If I do that, we have 0 is greater than 2 times 0 minus 2. So is 0 greater than -2? Yes, it is. So that means I shade everything above. So now I'm looking at where is there blue, orange, and green. So for this one, we have to be very, very careful. And there's a teeny tiny region where we have the overlap. I'm going to darken that in with purple. Notice this tiny little triangle right here. Okay, that's where we have blue, green, and purple overlapping. Okay, so that's the solution. In this problem, there's actually only a finite set of solutions, the only ones in that region, and that region is so small. So we do have solutions, but not as many as if I was just to talk about the blue and orange, right? Blue and orange would have an infinite amount because it's not bounded. It would go on and on. So if I asked you to list 3 possible solutions, we could look at these. One possible solution would be the ordered pair 3, 4, because that is one of the vertices and the green and orange lines are both solid, so that is included. I can't use the ordered pair 2, 3 because that has the blue line on it and blue is dashed, so it's not included. So the others are going to have to be decimals. So for example, 2.1 and 3.8, or 2.1 and 3.9. Okay? So if you put those into all of those equations, you would get true statements. You try number 1, and that one, it's nice. The lines are already in slope-intercept form. Make sure to graph them, do one at a time, do your shading, and then give 3 possible solutions. Solutions are what's in the shaded region. All right, and lastly, solving algebraically. So graphing is not always the best method because we don't necessarily can find the exact intersections if there's decimals and so forth. So substitution and elimination are algebraic ways to solve our systems of 2 variables. I'll do one of them each with you. With these, you do have to watch for your special cases, right? Remember, our 3 possible scenarios are that we actually get an ordered pair, we get no solution, 0 solutions, or we get infinitely many. So let's review with substitution first. So with substitution, if I do example 1 with you, we're trying to get a variable alone. So I'm going to isolate this y alone because that one is practically already alone, right? There's no coefficients. So to do that, I would subtract 2x. Now I take that and make sure you plug it into the other equation. Do not plug it back into the same equation. So I substitute it for y into the other equation. So now I have 5x minus 3 times the quantity of negative 2x plus 7 equals 23. Distribute and combine like terms. So 5x plus 6x minus 21. We add those together, we get 11x equals, add 21 over, gives me 44, so x equals 4. But we're looking for an ordered pair, so don't stop there. Now go back to find our y. So y equals negative 2 times x plus 7. This will give us negative 8 plus 7, which is negative 1. Don't just circle those. This is telling us we have a solution, right? We actually get an answer. And if we have a solution, it's an ordered pair. So be sure to now write your answer as an ordered pair. And there's my answer. Try number 2 using the substitution method. Okay, lastly, we're going to look at the elimination method. So I will do number 4 with you. For elimination, we need to make sure that our variables are lined up on top of each other. So we need to fix where I'm starring, okay? We do not have our variables in what we call standard form. So to do so, I'm going to subtract the 2x. We have plus 5y, and we have equals 10. Now those are lined up so that our x's are on top of each other, our y's are on top of each other, and our constants are on top of each other. Once we're at this point, we're trying to eliminate a variable. So I want to be able to add our 2 equations here together to have a variable cancel. What that means is that we need to have a pair of opposite coefficients. So to get a pair of opposite coefficients, I'm going to focus on the x's. And I'm going to say, okay, I need to multiply that second equation, that negative 2x plus 5y, by 2. That will now give me a positive 4x, a negative 4x, which will eliminate. So I'm going to recopy the original equation of 4x minus 10y equals negative 20. And now I'm going to rewrite that blue equation with distributing the 2. So now I have negative 4x plus 10y equals 20. Now I have a pair of opposites. The x's are opposites, so I'll add those together and we'll try to eliminate. So our x's cancel, gone. Y's, in this case, they're gone. And our constants are also gone. So in this problem, this is a special case. I get 0 equals 0. Is that a true statement? Yes, it is. So if I have a true statement, what that means is that I'll have infinitely many solutions. If it was a false statement, so 0 equals 9, then we would have no solution. And if only one variable cancels out, then you continue to solve and you actually solve for x and y and get your ordered pair. So you try number 3, again, making sure to use the elimination method.